this point here already. So to keep myself from rambling too much about this class and what it's about and what you're supposed to do, I put a PowerPoint together. So that will hopefully keep me on track. So this, I thought, would be a good place to start. So what to expect this semester is the first order of business. So what is this class about? Longitudinal analysis, broadly construed. How to analyze longitudinal data. And I tend to think about longitudinal data as something that is measured repeatedly about a person. But for those of you who study different types of entities, your units being measured repeatedly could be businesses, schools, classrooms, rats, plants. Anything else? Anyone else think of anything that you study longitudinally that I didn't say? No? People works as general? Okay, so just putting that out there. Likewise, repeated. We have all different kinds of longitudinal that are theoretically possible. The classic way that people think about longitudinal is a long-term study, so measuring like every year or every 6 months or something like that. But nowadays, the advent of smartphones and all kinds of other wearable devices give us moment-to-moment data. So it could be measured every second or every millisecond, even in the context of certain cognitive experiments, for instance. So regardless of what your unit is that's measured repeatedly, and regardless of how often that actually is, these models are going to work for you. So for those of you who do not know me, I don't like to scare people. I don't do tests, I don't like anxiety, and I don't want anyone to freak out that they're not good enough or not smart enough and that people don't like them. And yes, that is a Saturday Night Live reference for those of you who are old enough to remember it. So we're going to emphasize things from a very applied, practical, how to do it kind of focus. If you want to learn how to invert matrices, this is not the place for that. You can go elsewhere on campus to biostat or stat or public health or many other places where they have a slightly different focus on the same material, but I approach this from the need of a data analyst and the decision-making steps that you would go through and the programming that you have to fight through to be able to get the results of your analyses out. The hardest part about this topic matter, and of all the classes that I teach, I have been told repeatedly that this is the hardest, is because there is a ton of vocabulary. There are a ton of synonyms. So for instance, we'll talk about, variables that are measured once per person are going to be either macro variables, time invariant variables, between person variables, cross-sectional variables. All of those words mean the same thing, and there's more to add to that list. So to be able to communicate the results of your analyses with anyone, regardless of whether you're from psychology or management or botany, we have to learn all the words that go with the same ideas. And that combined with a new system of notation for the models that uses a multi-level structure, that's the part that people, I think, find challenging. It literally boils down to a working memory overload. So in this class, we will try to do a lot of repetition in terms of vocabulary drills and things like that to make sure that you can start automatizing all of these terms because that will make it easier. So the hard part is not the math. The computers are going to do the math for us. The hard part is actually the language and mastering all the different ways that we have to talk about it. So I think we can all do this. You wouldn't be here if you weren't qualified and ready to do this. And because this is an elective, you don't have to be here. So that means that you want to be here or somebody else wants you to be here, either way. And that's a great place to start from. So the way that I approach teaching, I try to divide the material into units, and each unit has a lecture that covers sort of the logic and the what and the why. And then there's an example or two or three or four that goes with each lecture that describes the how using software. And both of those things I think are equally important. My slides tend to have a lot of words on them. I will say sorry, not sorry. That is a deliberate choice because I want you to be able to listen and encode and reflect as much as possible and not scribble down equations. So I pack everything that I would want to say onto the slide so that you don't have to write as much. I would encourage you to get out a notebook or anything else that you might need to have white space to fill it with your own notes if that's something that's helpful to you. In terms of software, I'm going to focus on 3 different packages to try to keep everybody happy, but this is likely the last class that I'm going to try to do that because it's a lot. So SAS, Stata, or R, each of those packages can be used to do all of the work for this class, and I will show you every single example in all three packages that can be done. There are a few things that don't exist in certain combinations, but those are few and far between. And I will reinforce that even though the topic of this class is longitudinal, the way that I approach it is from the perspective of multi-level modeling, which is a much more general technique. And so if you learn longitudinal analysis, you're actually going to be learning a lot more than just that, because multi-level models run the world. All right, so like I said, I don't do tests, I don't do anxiety. I want everybody to get it eventually, and I don't really care how long it takes. I'm also going to start from the perspective of general linear models. That means regression or ANOVA. That's what I expect you to have familiarity with, and that's where we're going to start from, and then we're going to build onto that. So I don't presuppose that you know anything else. However, the next class after this, which several of you are in, can I get a show of hands who's coming back at 2 o'clock? A few people at least. The next class after this is structural equation models, which is quite overlapping with the content, but I'm not going to presuppose that you know that in this class. I will make connections back and forth when it's helpful, but I don't assume that is background knowledge. So what I will do is ask you to do 2 different types of activities. One is what I call a formative assessment, and this semester I have 7 of them planned, which is a bit more than usual because this class needs a lot more frequent review. And the way that this works is that you will log into Icon. They are listed under quizzes, although they're not quizzes. And there will be probably 3 or 4 open-ended big picture questions, vocabulary things, definitions, that kind of stuff. Questions that I hope that you should be able to answer off the top of your head or close to it. If you can't answer off the top of your head, go to your notes and figure out where it is. So this is an opportunity for not only you to give yourself a check on what you've learned and what you need to focus on, but also me. If I read through your answers and I see a lot of common misconceptions, that helps me know what I need to emphasize and what I need to go back over. So you get 2 points for doing each one of these at all. So I do read them, I don't grade them, but as long as you make some kind of effort, you get your points. So it's not really a quiz, it's just a structured review. We also are going to be doing homework, which is graded. There's going to be 5 of them instead of 6 this semester because they're long. So those of you who've had me before know what I mean, but I'll talk about that in just a second here. The first homework 0 will be available probably on Thursday. I'm waiting to make sure the rosters get all situated, and it will show you how to use the system. It is a custom online system that I built with help back in the day that allows you to do data analysis on individual specific data sets and get immediate feedback as to whether you're on the right track. So this semester, because it's very difficult to standardize individual data sets to make sure that you get through all of the concepts and techniques that I want, we're using canned data only. However, in the spring, if you come back, I'm planning to do an advanced longitudinal analysis class that will be more project-based, where you would get a chance to analyze data, get feedback on it, and learn about advanced models that are going to be immediately relevant to you. But this semester will be the building blocks that you need to be able to work independently. So if you have data that you care about, let me see a show of hands. How many of you have data that you care about right now that you want to learn how to analyze? A couple people? Okay, I'm going to call on y'all then, because if I say something and you're like, this makes me think of my data, can I see if we're talking about the same thing? Absolutely. Those are the best kinds of questions. If there is a topic that we don't cover this semester that you need to know to analyze your data, tell me about it. Odds are good I have an example or a paper or some other kind of resource that I can send you to help with that. So just because we're only doing canned data this semester, it's not to say I don't care about your data. I want you all to care about your data, but not everybody has it. So, all right, I'm going to take a drink because I just realized how fast I'm talking and ask if there's any questions or comments so far. No, we're good? Yes, sir.
I tried to access the textbook in the PDF version of the syllabus, and it sent me to like a bad link from Taylor and Francis. Do you know anything about that, or is
That's probably on me. I put a link to where the library version of it is, and I can double check that after class. It
That
should be
link-
on the website too.
That link works. It takes you to the library's page. Their link to Taylor and Francis leads to a broken page. If you're on the Taylor and Francis page, you can Google Lisa Hoffman, and the book will show up, and you can download it.
Okay. Okay, I did not intend for it to be that complicated. How about I just upload it into Icon? Does that work for everybody? Yeah, I'll do that. And then there's no worry about the broken links. But the library wants us to link to the library. That way they have like a metric of how many people have used it. They don't want us to upload things. But if they're going to make it difficult, then I'll do what I can. So, okay. Well, that's good to know. Thank you. Anything else while you're thinking of it? All right. So in terms of your work, everything is take home, open note, and untimed. You can take as much time to work on these things as you need to. I don't want people freaking out because they don't know something right now, because in this type of context, that's not necessary. That being said, I don't want you to become your own worst enemy and put things off. I know the rules. Things with hard deadlines get done, and things with soft deadlines get rescheduled. And I don't want to be in the rescheduled pile. So to encourage folks to complete the work in a timely fashion, it's 2 points off out of 100 for each late homework and 1 point off for a late formative assessment. That being said, your first trial homework 0 gives you 2 points extra credit for doing it. So it's like 1 free late homework. So if you're in a situation where you can't get it done on time, a 2-point hit is not that big of a deal. However, if you are planful, if you're looking at the syllabus and you're like, yeah, that week is going to be bad because I have X, Y, and Z other things in my life, send me an email, ask for an extension, and if it's requested at least 2 weeks in advance, I'll give it to you. Also, the syllabus as it is right now is my best guess as to how the semester will proceed, but if a topic takes longer than I had planned, I may push due dates to be later in the semester, but never earlier, because I want you to have at least a week or so after we've finished talking about something before the work on it is due. So the webpage will be the most up-to-date source. I will update it pretty much every single day with the videos from class or otherwise with schedule changes. The printable version of the syllabus I don't update as regularly. That's more for historical purposes, but by the end of the semester I'll have an updated version. All right, so the formative assessments, we talked about those. I also want to use those as a way to do some like case study type of things. So some of the questions might be like, imagine you're in this situation, what would you do? What would you recommend? What are the pros and cons? That kind of thing. So that way we can turn it into kind of a classroom activity without actually making it take up the whole time. So I'm gonna experiment with a little bit of that this year as something new. And then the homework, the way that homeworks work is that all of you are going to have a common story. Each of you is going to have an individual specific data set. I simulate the data using your ID number as a random seed, in fact, which is why I need your ID numbers if you're auditing the class. And I will ask you a question like, what is the estimate for the intercept in this model? And you'll type in what you think it is based on the analyses that you run. If you're right, it turns green. If you're wrong, it turns red. And you keep trying until it's green. That's it. Then once you have the right numbers, then you will proceed to a results section that has drop-down questions about interpretation. So for instance, if I asked you about a slope, a drop-down menu for it might be, is it positive and significant? Is it positive and non-significant? Is it negative and significant? Or is it negative and non-significant? And so you have to select the correct answer that goes with your data. So not everybody will have the same answer, but it's tied to what you got. And those, because they're multiple choice format, you don't get immediate feedback, but after the due date passes, you do get to see which of your answers are correct because they'll be in green. And if you got the answer wrong in red, what the answer should have been will be in green so that you can learn from your mistakes. And I'm happy to answer individual questions about homework after it's done, like why did I get this wrong? Or are you sure this is correct because I think it should be this? But I usually don't go over it in class unless everybody has finished it on time, which often does not happen. So I don't want to give away the story, so to speak. So yes, that's what you will see. The homework 0 that I will put up like I said, by Thursday, we'll give you a flavor as to what that will look like, and I will post a video of myself sort of going through it and narrating what's going to happen so that you can see what it looks like before we need to do anything serious. Sound good? All right, those of you who've done the homework before, can I get a, do you like it? Yeah? It's better than a test, right? Yes. And sometimes people have asked me, I do not know how many times you try a number before it's green. I don't keep track of that. So if you get it on the first try, good for you. If it takes 1,000 tries, stop, put it away, and send me an email. Such as that. So my job, answering questions. Please don't be shy. There is no such thing as a stupid question. Because if you ask a question in class, one of two things is going to happen. Either the people around you are going to be happy that you asked the question so they don't have to, or they're going to know the answer in their head, and then they're going to be happy that they knew the answer, and you'll make them feel good about themselves. So there's no waste in here. If you are shy, you can send me questions in the chat window. I have it open here with me in front of the Zoomers, or you can talk, or you can send me questions outside of class as well. I prefer questions in class, that way everyone can hear the answers though. Office hours. This semester I am doing office hours on Mondays and Wednesdays rather than after class, because 3 hours of me is quite enough, I think. And they will be on Zoom. So the way that office hours works is that I let everybody in, basically keep track of questions in the chat window, and I alternate across people to answer the questions. And so a lot of people tend to just come to office hours, hang out in the background and work, and then they pop into the chat window when they have a question, and then they can get help and keep working. So you're welcome to come to office hours and hang out to do your work. You're welcome to just show up randomly and ask a question. They will be from 3:30 to 4:30 on Mondays and Wednesdays on Zoom, and I do stay the whole time. So I will be doing that from home, since I'm not on campus those days most of the time, but I will be there the whole time. So if you want to pop in at 4:28, that's your right. I will always find something to do. In terms of homework, I use what I was taught as an undergrad, the 15-minute rule. If you're trying to make something work and it's longer than 15 minutes and that one thing is still not working, stop and send me an email. Particularly when it comes to troubleshooting syntax, right? One missing semicolon can set you back an entire day in SAS. In R, one missing parenthesis will do the same thing. And in Stata, you may forget your line continuer or some other trivial tiny thing that I have made those mistakes so many times, I can spot them at a glance. So the easiest thing for you to do to get help is to take a screenshot of whatever you're trying to do and what's not working and email it to me. If you want to send me your whole program, then that means I have to go to my computer and open it up and download it and look at it, which is a slower process. So that's fine too, but screenshots usually are a little bit more efficient. Readings. So this class does not have that many readings relative to the other class, and that's because I am relying quite heavily on the textbook that I wrote for this purpose. So I spent 5 years of my life churning out over 1,000 manuscript pages. My textbook is like 560 pages or something ridiculous, and yes, I wrote every single word. But I wrote it because I didn't feel like there was anything that I could teach from. So the book follows the class pretty well because I wrote the book from the class. So I use some of the same examples. I have extra examples that I'll show in here, but it should be helpful to fill in sort of the gaps. But because I don't want you to have just my perspective, I've added to the book with several articles about current best practices and other examples of the same kind of thing, papers that I've helped write and that kind of stuff. So I do think the readings will help you, but they are a lower priority relative to doing the coursework because learning by doing is the best thing that I can recommend for you. And then last but not least, practicing on data that you care about will help you. So if you want to use office hours to say, hey, I ran this model on my data, can I talk to you about it? Absolutely. That would be a lovely use of office hours as well. Okay, attendance. I'm not taking attendance. If you're going to miss class, that's okay with me. I trust that we are all grown-ups, that you all have your priorities, and that you can make good decisions about your time. Now, that being said, if you ghost me, right, if I don't see you for weeks on end and you don't turn in any work, then I might get worried and send you an email, but you don't have to worry about 1 or 2 absences. I am trying to be flexible in terms of attendance. If you feel like you might be sick, please use Zoom instead. It's not just me. I have a 7-year-old kid, and if I give it to him and he gives it to his school, like it's, you know, there's a contagion effect. So I appreciate that everyone is wearing masks. I'll continue to wear my masks, even though I don't love teaching in a mask, but this is life as we know it now. So do not worry that you're going to miss something if you're not able to be here in person, because I record everything. And on the off chance that I forget to hit record, which I'm checking right now just to make sure, which I sometimes do, I will redo the lecture offline and post that version of it. So even if you can't be here in person, if you can't be on Zoom either, you will still not miss anything. And last but not least, if anything needs to change, I will let you know by email by 9 a.m. on class days. So if, for instance, public schools are closed because of snow, I'm probably going to call class and say we're going on Zoom instead. I have a kid to take care of in that case, and I'm sure many of you have issues that crop up when schools are closed as well. So I will not hesitate to eject to Zoom only if we need to for health or safety. And you shouldn't hesitate either. You don't have to tell me which way you prefer to come. It's whatever you feel like on a given day. All right, software. So the 3 packages that I have pledged allegiance to, SAS, Stata, and R. And each of these things I know differentially well. So one question I get, why not SPSS? For a lot of what we're going to cover, SPSS is actually fine. It is on the website that goes with the textbook. So I also own the domain pilesofvariance.com. It was actually a birthday present from my husband, because I talked about wanting to have that for my book, and he went and bought it for me, because that's what nerds buy each other for birthday presents, is domain names and stuff. But the website that I spent another year building after the book was finished has SPSS code for every single model in the book. So if you're somebody who is diehard SPSS and you want to keep learning how to do longitudinal analysis in it, you could do it for a lot of it. Not necessarily all of it, but quite a bit of it. SPSS doesn't have as much room to grow, though. So for instance, if you wanted to embed your longitudinal analysis in a structural equation model and you had categorical or count indicators, like SPSS doesn't play that, AMIS doesn't play that. If you wanted to analyze binary outcomes instead of continuous outcomes longitudinally, SPSS doesn't have full information maximum likelihood for that. So SPSS has a lower ceiling than the other packages, which is why we don't tend to use it here. If you're somebody who likes drop-down menus, though, Stata has a really nice set of drop-down menus, and it does the same thing that SPSS does, in that after you go through and click your way through something, it writes the code to the window that you generated with your clicks. That way you can have it as part of your record. So I started out in SPSS back before it even had Windows, by the way. That's how old I am. SPSS used to be just code-based like the others. And I picked up SAS in my postdoc because everyone around me was using it, and I got really good at SAS. And then I had to teach a workshop one summer where I had everything prepared in SAS. It was for ICPSR at Michigan, and every single person in that room only knew Stata. So I had to learn Stata like instantaneously to be able to get through that class, and I've learned enough of it to be able to teach with it and feel pretty good about it. R is a whole different animal. How many of you are friends with R? Quite a few people. See, this is the way of the world. Everyone is heading into the R territory, so I've been dragged kicking and screaming into it against my will. Let's see, do we have a question on the Zoom? Allison?
Oh, no, sorry, I was saying I do R.
You do R. Oh, okay, you're raising your hand for that, yeah. I'm going to be honest with you. I hate R. I hate it. I hate how it's irregular, and there's 17 different packages to do one thing that SAS will do all of or Stata will do all of, and I'm still working on learning it. So odds are quite good that I'm going to show you R code and you look at it and go, yeah, I can do that in 1 line, but you're doing in 10? Great. If you know how to do something faster, better, or quicker, please tell me, and I will not be offended. I will be happy, because I'm trying to get better at R, even though I don't want to. So if you're someone who is already good at R, then I'm going to be working on making sure that you can use that for all of the homework as well. So I am assuming that everyone in the class knows how to use at least one of these packages, either SAS, Stata, or R. If you don't, that's okay, because by the time you'll actually need it, I hope that you will have a chance to go through some examples from my other introductory classes where I actually teach people from square one how to use these packages. So I also teach, I'm one of the people who teaches 6243, which is our like sort of first year. It's called Intermediate Statistical Methods, but it's a general linear models course. And that class, I have made several videos demonstrating how to just open the package and how to run SAS, Stata, and R, as well as a handout as to how to get to the virtual desktop. So virtual desktop is a software place that we can all use for free. It has SPSS, SAS, and Stata. R, of course, you can install on your own machine and you don't have to use it, but I have resources to help you figure out how to use these things if you haven't done that yet. In terms of considering what to focus on, here are some pros and cons. Stata does not have a free version as far as I know. SAS does, R does obviously, but Stata has a lot of really nice features that make it worth paying for, particularly if you're used to working with large-scale data sets and sampling weights and things like that. So there's my 2 cents about that. I'm trying to make everybody happy, which is why I have all 3 in the class. I'm using mostly output from SAS because the output part looks pretty much the same across the packages, but I will show code for all 3 packages for everything that we do. The website I referred to, pilesofvariance.com, has every single model that's in the book in 4 different packages, and people have started adding to it using R. This class uses R, but I haven't updated the rest of the website for that. In terms of homework, you can use any of the 3 packages. I've verified that the homework does work for that. You cannot use M+, though, for this, because it doesn't have residual maximum likelihood estimation, which is what we're going to be using for most things. You could use SPSS, but I'm not actively supporting it. All right, so then content for this semester. First up is a little bit of background. So concepts, vocabulary, and why would you want to go to the trouble to do this when repeated measures ANOVA is also available. That's the first unit of the class. The second lecture is I've decided to refer offline rather than give it in this version. So on the website here, I have a link to a review of general linear models from a previous class. If you weren't in that class, this is the generalized class. If that's something that you feel like you want to go back over, you can review those materials on your own, but I'm not going to go spend this class's time to it because I want to get to the good stuff. So the first unit really is just introduction, review of concepts, and how what we're going to do differs from repeated measures ANOVA. Then we get into what I call unconditional models, meaning just getting the time part right. So if you have change over time, what kind of change is it? Is it linear or is it nonlinear? And if it's nonlinear, there's like 6 different kinds that we'll go over in terms of what nonlinear can look like. If you have data that is where it's not so much change, but it's like day-to-day fluctuation or moment-to-moment fluctuation, those require a different type of model. But still, the idea is to make sure that we are adequately reproducing means, variances, and covariances over time before we add anything else to the model. And this takes a while. This is going to be the bulk of the class. And this is the part that can be skipped for cluster data or other types of data that use multi-level models as well. Then we get into conditional in the last unit, which in this class, I think we're only going to have time for time invariant predictors. The spring class will describe time varying predictors because to do them properly, you really do need to be in a structural equation modeling framework where you can do a multivariate analysis. So that is what's coming in the second half of this class, if you'd like to stick around. Okay, how are we doing? Am I scaring anybody yet? No, that's good. Not going for scary. Got some thumbs on the Zoom. We have a 3-thumb system here. We have thumbs up, which is self-explanatory. Thumbs sideways, which is like, and then thumbs down, of course, which is also self-explanatory. On Zoom, we don't have a thumb sideways or a thumbs down, but they could use like the poop emoji or something for that, right? You know, synonyms for thumbs down, they're plentiful on that, but don't be shy if you have questions. All right. Then, what kind of data are we going to learn about? In this class, interval. So, longitudinal models this semester are going to be focusing on conditionally normal outcomes. That's not to say that you can't do longitudinal models on others, but there are several extra pieces that you need to be able to do that in terms of link functions, alternative distributions, and alternative methods of estimation. That's something I hope to get to in the spring. We are working with observed variables in this class, and I am presupposing that the variable that you have measured over time means the same thing at each occasion. So if you're in a situation where like you have a test that changes over time, or each time somebody gets a different set of items, then you'll actually need to come to my second class because that's a measurement problem and solve that problem first before you can do the longitudinal analysis. So we're working with normal, supposedly continuous outcomes to start with, but everything that I have to say logically applies to other kinds of outcomes as well. We are also assuming measurement in variance over time. So that same kind of idea that basically that what you've observed means the same thing across time such that change is a reasonable goal. And a lot of people think that multi-level models or advanced statistics can somehow overcome basic problems of design. It cannot. So let me tell you a story of what I mean. As a graduate student, I worked in a research design and analysis unit the Lifespan Institute at the University of Kansas. And so I got a chance to talk with a lot of investigators about their data. And one particular project was concerned about having adequate measures that were sufficiently age-specific to show variability, right? Because you can't give the same measure to a 3-year-old that you give to a 12-year-old. Okay, that's a reasonable thing. But the solution that they came up with was to give different measures at every single occasion with no overlap. And what they wanted to do was z-score it. So compute a z-score at each occasion, and then they'd all be on the same scale. But the problem is that z-scores don't grow. You can't look at change from an apple to an orange to a banana. It doesn't work. So there wasn't a lot to be done in terms of measuring change because it wasn't based on the same information. Question, what if the tests are vertically scaled? That's what you need. So that's where the whole world of latent variable measurement models could have solved the problem had they had overlap. So like if I give tests A, B, C at the first occasion, then B, C, D at the next occasion, and then C, D, E at the last occasion, then you have a chance to link it all back together again onto one common scale. But you have to have overlap. So I may not necessarily be able to help you if you have design problems, but I will do as best I can. Will that be covered in the second class? Yes. The second class, I do want to be able to do longitudinal analysis on latent variables. So a variable that is defined by a measurement model, then watch that latent variable grow over time, as well as other permutations by which you can look at multivariate growth across latent space. So yes, that's the second class. But it requires all of the vocabulary, skills, and whatnot that this class covers to begin with. Okay. Thanks. You're welcome. Multiple occasions. That's the other thing we need. But I'm here to tell you, if you want to analyze 2 occasion data, ANOVA, go home. You don't need to be here. Because 2 occasion data I can't help you do much with. The problem is that if you think about giving each person their own growth curve, right, their own individual trajectory, and you got 2 points and you draw a line between them, how well does that line fit those 2 points? Perfectly. So you can either have perfect measurement of change or everybody changes the same with some error, but not both. So with only 2 occasions, there's no way to differentiate what is individual differences in change, which is sort of the big deal in this thing, from just error. 2 occasions is not really enough to do much with. If it's a pre-post design, I would say put it in a multivariate model, give each occasion its own residual variance with a covariance, and go about your business. More data is always better. So as somebody who gets asked to participate in grants, I often get the question, how many subjects do I need? You know what my answer is? More. How many occasions do I need? More. Always more. With the exception of certain folks I've worked with from sociology that have like data sets with like hundreds of thousands of people. Okay, they need less or fewer. I'm not sure which it is. But more is generally better. And the thing that makes these models tricky in terms of anticipating power and sample size considerations is that it's more of each kind. So the more occasions you have, the better shot you have at tracking nonlinear change. You don't have to just assume it's just a straight line. And the more information you have to summarize each person's trajectory to get a better, more reliable estimate of their change. But the more people you have, then the better chance you have to be able to quantify how much of the variability is because people change differently, and then to predict it with person-level information. And more generally, the same thing is true for these models when you extend it into, say, multiple types of outcomes over time, or people who are nested in multiple groups, or any other of these sorts of complex sampling. You need more of the dimension that you care about for prediction. So if I have students nested in classes, and I want to look at classroom level predictors, I need a lot of classes, not a lot of students. So it gets tricky real quick, but 2 occasions is not really going to be that interesting. 3 is the bare minimum to be able to use most of the models that we'll talk about. So here is a picture from a very classic article that's on your reading list that describes how the number of occasions and the amount of signal relative to noise can influence the reliability of change. And 2 is barely enough. So if you have barely any signal, 3 is definitely going to help. 3 definitely helps if you have medium signal, and more is better up to some point. More people is better in terms of being able to quantify how people differ from each other. All right, vocabulary, levels of analysis. So your first set of new synonyms. In thinking about longitudinal data, I am going to start with the type of design where we have occasions nested in persons. They don't have to be the same occasions across persons, but they could be. And in that basic type of design, which I would consider to be a 2-level sampling design, because you have multiple occasions per person and multiple people, we would refer to differences between people as between person. Level 2, macro, inter-individual differences. All of those words are synonyms in this context. So every longitudinal study that starts out as a cross-sectional study of one occasion has this kind of information. If you took general linear models with me or generalized linear models with me, this is all we talked about. Why do some people have different outcomes from each other? Oh, I don't know. Let's put some predictors in and find out. That type of variation between persons is always there. The extra component that you get is actually the level 1 component in this context, the time component. So that's within persons, the micro level 1, intra as opposed to inter, or time varying. All of those words mean the same thing too. So if I'm talking to a statistician, I might talk about level 2 random effects and level 1 residuals. If I'm giving a job talk to a general audience, I would talk about examining inter-individual differences and intra-individual change. It's the same. So the extra part is the level 1 part. That's the part that we focus on. And what's very tricky about predictors in particular is that just like outcomes, they're going to have some of both. Some people are going to be different from each other all the time. They start out higher and they stay higher. But people also change within persons. So the extent to which a variable is both between person and within person at the same time is what makes these models really complicated. So the model for the variance is the thing we focus on most, the term I'm going to introduce here in just a second. All right. Questions or comments thus far? Any other terms that you've heard that you want to throw to my list as synonyms? No? Now, once you get better at multi-level stuff, then what's level 1 and level 2 is going to be based on your design. But it's really super hard to move that around when you're first learning these things. So for this semester, time is level 1 and people are level 2, the end. For those of you who have learned about multi-level models in the context of clustered data, you can substitute person with cluster or group, but the label between and the label within stays. Between is always 2 and within is always 1. The question is between and within what? What is the thing that you have multiple measures on? Is it a cluster? Is it a person? Is it an animal? Etc. In terms of kinds of longitudinal data then, I like to think about this as belonging to a spectrum with 2 endpoints as demonstrated here. So if you are in sort of a classical longitudinal study where you have sampled people at occasions deliberately long enough to where they should have changed. So like if you're in a hospital setting and you're looking to see if a new drug works, you might sample them every month. If you are looking at decline as a function of aging or Alzheimer's or any other sort of pathology, you might sample them every 6 months or every year. But this type of analysis where you're deliberately sampling occasions so that people will have had a chance to change, and you're interested in predicting why people change differently from each other, that is sort of your classic, what is known as a latent growth curve model. Now let me take apart each of these words here for a second. Model means a description of how variables relate to each other. Growth curve is what it is always called, even if you are studying a phenomenon that declines linearly. It is always a growth curve, and I don't know why, but that is a terminology that people have just accepted. Latent is if you are estimating the exact same model using structural equation modeling software instead. It sounds fancier, but it's not different. You would think that a latent growth curve model would refer to change over time in a latent variable, but you would be incorrect. That is a second order latent growth curve model for the spring. So one of the things that's tricky about this is being able to specify the right kind of change for each person that does a best approximation of recreating the variance and covariance over time. So to the best of my little PowerPoint drawing ability, if you have different slopes for different folks here, that necessarily means your variance has to change over time. People spread themselves out as they grow or they get closer together. And if variance changes over time, covariance is going to change over time too. So a big component of fitting these models is making sure that our model for time accurately represents the heterogeneity of variance that time is creating. On the other side of the continuum here is what I call fluctuation. And this is where time is just a way to get a lot of data. So ecological momentary assessment studies, what used to be called like daily diary studies before we had technology, people who wear like the Fitbits and the what do you call the thingies that record your walking? Accelerometer, is that the right word? Does that sound right? Yeah, well, yeah, but it's like the clinical version of it. I feel like accelerometer is a word. Well, okay, I'm a psychologist today. I'm a health psychologist. I'm just going to call it that. But you get lots and lots and lots of data. And the goal isn't to see change. The goal is to see how things co-vary together. So if I get a crappy night of sleep, does that mean I'm less likely to exercise the next day? And if I'm less likely to exercise, am I more grumpy with my kid? Like all of these sorts of within-person things that are going about their own rhythms, we're not trying to make it better or fix people. We're just using time as a way to get a lot of information about the person. So we might have growth curves, so to speak, that look like this, where time on the x-axis doesn't really play a role. It doesn't matter if it's day 1 of the study or day 6 of the study. It might matter if it's 8 a.m. versus noon. And so if that's the case, then you're back over here again. But one thing that's extra that we have to pay attention to in this context is differences in variability. So some people may have different, say, moods, like some people may just be happier people, but they may also differ in the extent to which they're moody, right? The idea of being reactive or volatile. Some people go like this, and some people are more even keel. That can be operationalized as an individual difference in variance, which is an extra cool thing you can do with these sorts of models. So the idea of examining relative changes, like if I'm grumpier than usual, what happens? If I'm more stressed than usual, what happens? How does that change my consistency of behavior or my subsequent behaviors? Those are usually the kinds of questions that this type of study is designed to address. But we still have to get the time component right first so that the story isn't just, well, it's Monday and that's why. What else after controlling for biological rhythms, schedules, and that kind of influence of time? Most of the time, we're somewhere in the middle. People may expect to see change, but then nobody changes. Or they may expect that it's just fluctuation, but then there are cycles or rhythms that have to be accounted for with respect to time. So we will cover all of this ground in terms of what to do in these situations and what are the concerns that you would want to address, how to let the data help you figure out what the model should look like as opposed to just relying on theory. It should be a combination of both. So we'll cover the whole spectrum of this kind of stuff. All right, time, change over time, just to give you a little bit of thinking. Time is one of those variables that isn't really an explainer, right? It might be a predictor in the model, but time doesn't really cause anything. It's what happens as time is unfolding that matters. And one of the things that you'll have to sort out in your own data is what is the relevant metric of time? It's not always obvious. So let's say that I'm interested in looking at elementary school children and various outcomes. If I were interested in an academic outcome, then what grade they're in is probably the most relevant metric of time. Are they in second grade, third grade? Because then I have some expectation as to what they have been taught and what they should know. But if it's something like, onset of puberty, well, then what grade you're in probably doesn't matter as much as how old you are and other various physical characteristics. And so then chronological age might make more sense as the time mechanism that would be sort of responsible for what's happening. If I'm studying the pathology of a disease, for instance, let's say that you're studying something like a progression of cancer. When you're diagnosed and how long you've had the disease is what's relevant, not necessarily how old you are or what grade you're in. So this is something that you'll have to figure out for yourself. The models that I focus on tend to just talk about time in terms of how long have you been in the study, where 0 is when you got there, and how long has it been since. Because those models are theoretically agnostic and they can't be wrong. But it's up to you to think about, what does this translate to in terms of my own data? For fluctuation types of data where you're not expecting change, you still may see it. So it may matter whether you're answering questions on your survey on a Monday afternoon versus a Friday morning or a weekend. It may matter how long you've been in the study if you're tired of answering the questions and you start making the stupid thing go away, right? So if data quality deteriorates over the course of a study, then you might want to pay attention to what study day it is. So those are sort of some sneaky time metrics that show up that we'll have to deal with. When it gets very tricky is when time varies both within and between persons. So an accelerated longitudinal design, is this a term you guys have heard before? Accelerated, also known as a sequential cohort design or an overlapping cohort design. So accelerated designs try to do longitudinal research in a shorter amount of time. So like if I wanted to study elementary school, I could round up a bunch of kindergartners and follow them until they finish 6th grade. Or I could grab kindergartners, first graders, and second graders and follow them each for less time. So I can string together all of elementary school by sort of pitching the trajectories on top of each other. That works sometimes, but not others. And so one of the issues that we'll deal with in the advanced class is how to make sure that between person differences in where they start and within person differences in time that's elapsed have their own roles in the model. And then last but not least, terms that you will hear me say over and over again is whether the data are balanced with time. So the way that I use these terms is talking about the presence of a shared measurement schedule or not. So if the set of occasions you could possibly have is the same across people, I call that balanced. So if everybody gets tested at pre-test, and that's 1 day. And everybody gets tested at post-test, and then everybody gets tested at follow-up. And everything happens at the same time, that's balanced. If I measure you at the first occasion, 8 weeks later, and then 6 months after that, still balanced, as long as everybody's on the same schedule. So not necessarily equal interval, but just everybody has the same possible set of occasions. If you have balanced data, or it's balanced enough to pretend like it is, you have a lot more choices. You can have, there's just a lot of things that are neater and easier and tidier with balanced data. But one of the benefits of the models that we'll go over in this class is that you don't have to have balanced data. So I'm going to have my phone buzz you 4 times a day and answer these questions. That's unbalanced, because what times they happen to be are going to vary as a function of when the beeps happened. If you think you have balanced data, maybe you don't. So if you go into a school and you want to have a fall observation versus a spring observation, do you think it matters if fall is August or November? I would hope so, right? Otherwise, the kids haven't learned anything for 3 months. So maybe it's not really fall. Maybe it's August versus November versus January. And so then we end up with an unbalanced design because of the way that the data were collected. So balanced has one set of possibilities, unbalanced has another. And the nice part about the random effects models in particular is that they work either way. It's just a little bit easier and tidier if you have balanced. Okay, thoughts or questions on that? All right, okay, so switching gears a little bit from design to modeling. I'm going to introduce a way that I see the world that is going to be very, very important in this class. The 2 sides of a model. There's what I call the model for the means, and the other side is going to be the model for the variance. This is not something that I have talked much about if you had me for earlier classes than this, because it wasn't relevant. So I'm pretty sure that in your head, when you think model for the means. Model for the means is, okay, what predictors do I have? How do they relate to my outcome? Do they have linear effects or nonlinear effects? Or how many slopes do I need if it's a categorical predictor? Do they have just main effects, or are they part of interaction terms? All of that kind of stuff. The idea of how predictor variables relate to outcome variables and the specification of that relationship. That's the model for the means. All of those terms previously have been what I'm called fixed effects. And if you had me for general linear models, I used that term deliberately because I knew another kind was coming. But if you learned regression from someone else, they might have talked about intercepts and slopes, for instance. Those are fixed effects. The word fixed in this context means a constant. Everybody gets the same. Like you run your regression and your output comes back and it says the slope is 2. Okay, that means that y goes up by 2 for every 1 unit increase in x, and that happens the same way for everybody. It's a fixed effect. So the fixed slopes that you're used to thinking about are estimated constants that multiply known predictor variables. That's the model for the means. Another synonym for that is the structural part of the model, or the linear predictor in generalized linear models class. The other side, and the side that makes this class uniquely challenging, is the model for the variance. Synonyms for this have to do with the error side of the model, the variance side of the model. If you want to sound fancy, the stochastic side of the model, the random effects, and the residuals. So for instance, back in regression land, when you write out a single level regression model, y equals slopes and intercepts and stuff, there's something at the end of the model. What's at the end? What letter? Error, right? Usually an E or an R or maybe an epsilon if you're going Greek. And you're told that you have to believe certain things about that E in order for your results to be accurate. In a linear regression context, those E's are supposed to be independent, that's the big one, have constant variance across everything, and they are supposed to be normally distributed. Well, what if that's not true? In longitudinal data, 2 of those are not going to be true almost right away. E's from the same person are going to be related. I can guarantee it. People have a commonality in how they do tasks and answer questions always. In longitudinal data, there is going to be a very strong component that makes the residuals related to each other. So how do we build that into the model is the question. Likewise, if people spread themselves out over time by changing differently, then the variance can't be constant either. So right off the bat, we're into this sort of what's called non-independent or dependent, meaning correlated residuals with different amounts of variance depending on what time it is. So the big way that longitudinal analyses differ from cross-sectional analyses is in this extra focus on the residual part. To put it in a more summary way, we have to figure out what all the different reasons are why the residuals would have had different variance and been related, and build those reasons into the model. Those reasons become random effects in most cases. So that's the big part. It's like that E at the end that you just sort of took for granted. That's going to be the star of the show. All right. More words to go with the same idea. I want to give you all the terms that you could help Google, basically, to try and learn this stuff on your own. So more words that go with these same ideas. One distinction that we can make about the label for a model is general versus generalized. So the term general actually means something very specific. It means conditionally normal. That's what general means. It does not mean general. If you tie the word "ized" on it, that is how the model has to adapt to be able to predict things that are not conditionally normal. So that is the addition of what's known as link functions, which are transformations of the conditional mean, and different distributions. So if you've heard of logistic regression, for instance, or count regression, negative binomial regression, proportional odds models, like all that stuff, that's a generalized model. But what these both have in common is that they're designed for data that have one dimension of sampling. Between person differences only. Each person contributes one outcome and therefore has one residual. Where we're headed is when you have to adapt the model to have multiple dimensions of sampling or multiple layers of sampling, such as occasions and persons at the most basic case. Then we can throw the word mixed into the name to convey that idea. The term mixed means the addition of fixed and random effects, where fixed effects, again, are estimated constants. Random effects are estimated variables. A random effect means everybody gets their own. So we'll have a lot of new vocabulary in the case, but the term mixed means both of these things together, which is necessary whenever you have more than one dimension of sampling with unexplained variability. And linear is a word that shows up in all of these, and what it means is that the form of the equation is slope times variable plus slope times variable. So that can be easily done in many software packages as opposed to a nonlinear model, which is a lot harder to estimate, but what we will see as well. So this class is also about general linear mixed models or mixed effects models to be continued into the ized section in the spring. I do teach a class on generalized linear models every spring. And if you haven't had that, I would recommend that because it will make the rest of these advanced models a little bit easier to handle if you've seen link functions and conditional distributions like that before. All right, more word salad and then we'll call it a day. How about that? Fair? You're like, come on, Lisa, it's the first day of class. You're going to keep me the whole time? No, I'll let you out like 2 minutes early. I wish I could be one of those instructors that like we meet on the lawn when it's a nice day and stuff. Like I always wanted to be one of those people. I'm just not, you know. But hopefully you can get outside for a little bit. It is very nice out there. So the models that we are using to analyze longitudinal data are multi-level models. That is my preferred term because I think it's the most descriptive and the most general. But it is the same thing as what is known as linear mixed effects models, random coefficients models, or hierarchical linear models, HLM in particular, There's a software package that's called that does these models. All of those words mean the same thing. It is the idea of fixed effects of predictors plus random effects that give you extra layers of sampling variability whenever you have more than one kind of sampling at the same time. And there's an expression that if you have a hammer, everything is a nail. Everything is a nail, I swear to you. So here are all the ways that multi-level models get put into other types of contexts. So if you've done a random effects ANOVA or repeated measures ANOVA, that is a special case of a multi-level model with only a random intercept. If you've done latent growth curves, that's where we're headed this semester. And the intersection between what I call multi-level and single-level structural equation models is something that we will talk about a little bit and build on that definitely in the spring in the advanced class. Ecological momentary assessment or fluctuation models, these are special cases. And now there's a whole new set of words that there's more than this even, but dynamic SEM or multi-level SEM is multivariate versions of these same models. If you have clustered data, these models work for that as well. So if you have students nested in teachers, nested in schools, nested in districts, that kind of thing, then what the levels mean is different, but it's still between and within, and the same ideas apply. Cross-classified models or cross-random effects models. Generalizability theory is a bunch of multi-level models as well, for those of you in the measurement cohort here. Value-added models in education are based in multi-level models as well. And last but not least, everything you know about psychometrics and measurement is a multi-level model. Seriously. Item responses are nested in people. Boom. Theta is a random intercept. Factor scores are random effects. So because of that intersection, all of this is kind of the same, but the way that people talk about it, the reasons they do it, and the software they use for it are what's different. So I think that you will find, even if you only came here to learn longitudinal, that you accidentally learn some of this other stuff too along the way, because it is the same under the hood. All right. Yes. So a brief aside here. Why do I do multi-level? Because it's easier. Because I can start from a regression model and add stuff to it. And I find that a lot easier to wrap my head around than going into the world of structural equation models and then describing how you can trick the model through constraints to become a longitudinal model. So yes, I could have taught this class from the basis of SEM. I'm deciding not to do that. But we will end up with the same types of models being estimated both ways. So multi-level to start with because it's easier. That's my pitch. The rest of this is the sales pitch that we will get to do next time. To make sure you come back. What can multi-level do for you? If you act now, I'll throw in, I don't know, maybe I should bring soda for the whole class. That would take a lot in my bag. Anywho, 1:42, I promised 2 minutes early, so I got 1 minute for questions if anyone has any. Are you excited? You gonna come back? I hope so. Okay, well then let me know if you need anything. Otherwise, I hope to see you either as a roomer or a Zoomer on Thursday. Peace out, everybody.